Well, there's not a whole lot to kind of report today. We're at the end of the week. I didn't get to see you guys yesterday. We are going to go ahead and move on with the new lesson today. The test, we talked about that on Tuesday. I passed those back. If anybody was wanting to retake, you still have plenty of time. The deadline was going to be Wednesday by 8:05 in the morning. So you still have until, halfway through the week next week to go ahead and get that taken care of. By next week, I'm hoping on Tuesday I can go ahead and introduce you to the unit circle and finally show you the patterns and how it's constructed so that we can really start evaluating those 6 trig functions on that as well. And, we'll just continue to move forward. I mean, I've already got a quiz for next week over this lesson right here. And I don't think there's anything really special about next week. It's just a normal week. Okay. Nothing going on. So let's see what we're talking about today. So a little bit of this is going to be familiar to you, hopefully, from geometry. We're going to be doing it in a different way. In geometry, we found if given a central angle and the length of the radius, we could set up a proportion to find the length of an arc in a circle. The arc length is a fraction of the total circumference. Remember, the circumference is the total distance around the circle, and the central angle is a fraction of 1 full revolution. So when we're talking about arc length, let's say we have 2 points on my circle. Arc length is the distance between them on the circle. That's why, we're only taking a portion of the circumference, the full distance around. Likewise, from geometry, we know that the ratio of the measures of the angles equals the ratio of the corresponding lengths of the arc subtended by these angles. So again, we have another one of those mathematical definitions that's about as clear as mud. You had to read it a couple of times to make sure. But in other words, we're going to go ahead and take a ratio of the angles, just like we were talking about here. So theta to theta sub 1 equals S to S sub 1. And now we're referring to S as that arc length that we're looking for. Okay, so it says here, if we go ahead and let theta sub 1 equal 1 radian, so theta over 1, I'm just replacing it, equals, then we're going to go ahead and replace S sub 1 with R, so I have S over R. Well, how do we solve a proportion? We cross multiply, right? There we go. So 1 times S is going to give me S, which equals the radius times theta. So here is a formula. So back in geometry, more than likely you used a proportion to go ahead and find arc length, even area of a sector. But now that we know about radians, we're just going to go ahead and say that the arc length S is equal to the radius times theta. And the only thing you need to make sure of is that theta is in radians, never degrees. Okay? Always has to be in radians for the formula to work. All right, well, let's go ahead and put it into practice. Let's see what you guys think. We'll start off with some pretty easy ones because the majority of what I want to talk about today is linear and angular velocity. I want to help you become familiar with those. So it says, example 1, given a central angle of 60 degrees and a radius of 8 centimeters, find the length of the intercepted arc. Okay, so I've got a circle over here. Okay, and I really like these circle problems because they do get around. Okay. Probably sitting out there, wheelie, Mr. West, in the first wheelie. Okay. Yeah, you missed it. Okay. So we got a radius of 8 centimeters. Okay. We've got an angle created that's 60 degrees. So let's go ahead and say maybe 60 degrees is right here. So we're looking for this length created by that angle 60 degrees. Remember, the arc length is always S, right? Well, that's really easy. All I got to do is multiply the radius by the angle. So I know 60 times 8 is 480. Done. Right? Or am I missing something? Oh, no, that's close. And that's if we're looking for area of a sector. But what was the one thing that I just mentioned? There we go. You have to have theta in radians, not degrees. So before I multiply the two together, I need to go ahead and convert it. Okay, so 60 degrees, I'm going to put that over 1. What is the conversion? Pi over 180, yes. So pi over 180. So you'll notice these degrees are going to cancel. So 60 is the common factor. 60 divides into itself once, but into 180 3 times. So pi over 3 radians is equivalent to 60 degrees. Now that it's in radians, I can go ahead and apply my formula. Okay, so S, the arc length I'm looking for, is going to equal the radius, 8 centimeters, times the pi over 3 radians. So if I multiply as is, remember we can put that over 1. That would just be 8 pi over 3. But you know, a lot of times I'm going to ask you to approximate to a certain decimal place. So let's say to the nearest tenth. Let me come on over here. I'm going to hit Control Divide for my fraction. So 8, and I like to use this button down here that's actually labeled pi right down by h. Okay. It also gives you a bunch of other great characters if you ever need those, but 8 pi divided by, what was it? 3? Okay. So now if I go ahead and push enter, I know that that arc length is roughly about 8.4 centimeters. Okay. Questions on that? Okay. So about 8.4 centimeters. There you go. The radius times your angle measure. You just have to make sure that the angle is in radians. Okay. That's all there is to it. Okay. And by the time you're done, you'll see that everything comes full circle. Yeah. I have another really good one. Let's see if you like it, and we'll get there. Okay, example 2. If a 100-degree arc of a circle has a length of 9 inches to the nearest inch, what is the radius of the circle? So this one, see, we're working backwards. Okay, we're not given the radius and the angle measure. We're given the actual arc length, and we want to use that to find the radius. So we have S is equal to R theta. So let's go ahead and draw this. We have a 100-degree measure. Okay, so 100 degrees is bigger than a quarter, so I'm going to go ahead and say maybe something like that. Okay, so they're already providing me that this arc length right here is 9 inches, and we don't know what the radius is. Okay, well, I would go ahead and plug in everything I have, but there's something specific this formula needs. Remember, theta has to be in radians. Okay, so the first thing, just like the last time. Okay, whoop, could have let me write it. 100 degrees over 1 times, well, we're going to multiply by pi over 180 degrees. So again, the degrees cancel. What is 100 1/80ths? 5/9, yes. Okay. And we can break it down. If you take away the zeros, you get to 10/18, and then from there. Okay. So we have 5 pi over 9, or 5/9 pi. Okay. So now let's plug in what we have. So the arc length S, 9, is equal to the radius times theta. So I'm going to go ahead and put 5 pi over 9 times R. Sorry. Now, all we need to do is solve the equation. So normally in an equation like this, you go ahead and divide by the coefficient, right? But the coefficient is a fraction. So what happens if I divide through by a fraction? What's that the same as? Okay, dividing by a fraction is the same as multiplying by the reciprocal. Yes. So I can go ahead and multiply this by 9 over 5 pi. 9 over 5 pi. Because you notice we can put this over 1. So the 9's will cancel, the 5 pi's cancel. There's the R that I'm looking for, right? So now just multiply straight across, I'm going to get 81 over 5 pi. Now that's the number of inches. That is going to be the radius. But it does say it wants what? Okay, to the nearest inch. So let's see what that would actually be. What do we have? 81 over 5 pi. Okay. And it is doing it again. It's been doing it all morning. So let me go ahead and click on this pi right here. Okay. All right. So what's to the nearest inch? What would that be? I'd say about 5 inches. Because, you know, to the nearest tenth would be 5.2. That's still pretty small. So 5 inches. There we go. Now, remember, there are other ways you can solve problems like this. If I had, you know, 9 is equal to 5 pi over 9r, you could simply go ahead and multiply both sides by the denominator. 9 times 9. So you get 81 is equal to, those cancel, 5 pi r. And see, in order to solve for the radius, you would still go ahead and divide through by 5 pi. So see, you're still going to end up with the same thing. It just really depends on what you want to do, what you feel the most comfortable with. Okay. Questions? Okay. All right. Let's try example 3. It says find the angle in radians, then convert to the nearest degree. So we don't know what theta is, but they do give me S, which is what? 8. Remember, that's the arc length. And they're giving me R, the radius 5. So S is equal to R theta. Okay, so the arc length 8 is equal to the radius 5 times theta. And what would theta equal? Theta would have to be 8/5. Now remember, the only way that this formula works is if theta is what? In radians. So in this case, to have the arc length and the radius, this already has to be in radians. Okay. So that already has to be in radians. Because if I multiply 5 times 8/5, it should give me an arc length of 8. So it has to be in radians. All right. But now the problem wanted me to do something. Yeah, so we found it in radians. We now want to convert it to the nearest degree. All right. 8/5 times 180 over pi. Yes. 180 over pi. Remember, if you want to convert degrees to radians, you multiply by pi over 180, just like we did. If you want radians to be degrees, you multiply by 180 over pi. So let me come back over here, document B. Let's see if it'll work. We are going to take 8 over 5 times parentheses, control divide, 180 over. Let's see if it'll work this time. It is not working. Okay. I don't know why that one little section is not working, but that's okay. I'll just run over here real fast. There we go. All right, so let's see what I get as soon as I push enter. 91.67. So to the nearest degree, what would you say? I'd say 92. About 92 degrees. There you go. Is anybody having a hard time? Anybody not sure where I'm getting these values from? Okay. Arc length, not too bad. Okay. Again, you'll probably remember, seeing that in geometry. It's just that now we're using a different formula because we actually have a knowledge of radians. Okay. So now let's go ahead and put that aside for a second. Let's start talking about the main topic for today, linear and angular velocity. Have you ever thought about math while out for a bicycle ride? Sure, we all have. You know how to find your average speed by calculating distance traveled and divided by the time from long ago. So do you guys remember this formula? Distance is equal to your speed r times t. In fact, I go back far enough. My teacher, when I was first introduced to this, she referred to it as the dirt formula. Did any of your teachers ever call it that? No? Okay. But, I'm sorry? What did you say, Brent? Okay. Okay. So distance equals rate times time. So we're going to be using this idea here, but in trigonometry, we're going to call this linear velocity or linear speed. Okay, so normally, one of the things we're going to talk about in the second semester is going to be something called vectors. Okay, so it represents speed, but it has to have a direction, right? Okay, well, when we're talking about linear velocity, we are still trying to find the speed that an object is moving, but we're finding how fast it is in a circular path, how fast something is moving around in a circle. Okay, so it can still be on any unit of measurement that we want. Okay, we're just going to go ahead and replace some of the variables. Instead of the speed, we're going to go ahead and say v. Okay, v is now our linear velocity, and s is still going to be our arc length. Okay, the distance that we're looking at. Okay, so let's go ahead and put it all together with a problem. Let's start to see this come together. Example 4. It says, if you travel in a car at 65 miles per hour, how far did you go in 10 seconds? Okay, now here's the thing. My speed is in miles per hour, right? So if I'm looking for distance, what has to drop out? Yeah, the hours. I got to get rid of the time. But we have another issue. This is in miles per hour, and we're asking the question in seconds. Okay, so changing those units of measurement, that's what we call dimensional analysis. So I'm going to start with what we have here. 65 miles in 1 hour. Okay. Now we're just going to go ahead and take this one fraction at a time. Now I want the miles. Okay, I definitely want to keep that, but I want to change hours to seconds. So what's between the two? Okay, so I got to change hours to minutes. Now, if I want the hours to cancel, I'm going to have to make sure that the hours alternate. Okay, and I'm going to put the minutes here. And what values am I going to use? Yeah, 1 hour is 60 minutes, right? Okay. So right now, if I were to stop, it's going to be in miles per minutes. So I have to go one more fraction because I want miles per seconds. So now I want the minutes to cancel. So I've got to put those above with the seconds down below. So again, 1 minute is 60 seconds. So if you look overall, your hours are going to cancel. Your minutes are going to cancel. So you're left with miles per second. This is what we call dimensional analysis. You know, maybe I mentioned it before. Some of your teachers in the past would have called it train tracks. Does that sound familiar? No. But have you seen something like this before, maybe in chemistry? Okay, doing stuff like that. Good. Okay. Now, some people have asked me in other classes today, you know, if you feel really comfortable with it, I would encourage you to do this. If not, you know, go ahead and write it out. The question's been asked, could I just go ahead and put one fraction here and say 1 hour is 3,600 seconds? Because you see 60 minutes at 60 seconds per minute. So 1 hour is 3,600 seconds, right? So if anybody in here wants to go ahead and maybe shorten their analysis a little bit by taking those, things like that, if you feel comfortable, please go ahead and do it. I always prefer to go ahead and write it out. So even on lessons, I'm going to be doing the exact same thing. Okay. So all I need to do is divide 65 by the product of 60 and 60, which is the 3,600. So 65 divided by 3,600. Okay. So I'm getting about 0.018 miles per second. Okay, so about 0.018 miles per second. Now the question is simply asking me, okay, what's the distance you're traveling? So if you think back to that formula, it's the speed times your time. Well, here's the speed, and here's my time. See, those seconds are going to drop out just like I wanted. The distance equals RT. So my speed, we got 0.018 miles per second times the time, 10 seconds. Okay. And you'll notice what happens. Yeah. And this one, you know, we probably don't have to go back to the calculator. If I multiply by 10, what effect is that going to have? Yeah, it's just going to move it over 1. So I'd say we're looking at about 0.18 miles is how far you traveled. That's what we call dimensional analysis. And when you're looking at solving linear and angular velocity problems, this is going to come up, you know, quite a bit. You'll have it with respect to time, distances, all that good stuff. Okay. Does anybody have any questions on that? Okay. And if you're a little hazy on the dimensional analysis, you know, don't worry. We're going to be looking at plenty of examples. But now let me go ahead and introduce you to angular velocity. Okay. Now, linear velocity, linear speed was how fast an object is moving, but what? How fast it's moving in a circle if it's following a circular path. Well, go back to the example on the bikes. Think about how fast the wheels are rotating as you're riding your bike. This is what we call angular speed or angular velocity. We use the Greek letter omega. Okay, looks like a curvy little W. That's the variable that represents angular speed. So this is the rate that measures changes in the wheel's central angle theta over time. So if you're thinking about a circle here, okay, you know, you're spinning so fast, this is how fast the angle is increasing with respect to time. That's angular speed. Linear speed is actually how fast the object is moving on a circular path. Okay. With angular speed, it's how fast the angle is increasing with respect to time. Now, the thing about angular velocity, it's always, always, always the same. We always have it in radians per time. And this could be anything. It could be per second, per minute, okay, per hour, whatever. Okay. But it's always, always going to be radians per time. All right, well, let's take a look at example 5. Okay. It says if a central angle spins 15 pi radians in 8 seconds, how fast is the angle spinning per second? Round to the nearest thousands. Well, I'm telling you, that angular velocity is always radians per time, right? Well, what am I provided in the problem? The number of radians and the amount of time. So all I have to do is set up that fraction. So this would be 15 pi, okay, I'll go ahead and say radians, over 8 seconds. Okay, it's always radians per time, and the time can be whatever you need it to be. All right. Well, let's go ahead and figure out what that is. 15 pi divided by 8. And the nearest thousandth, how many decimal places is that? 3. Okay, so 15, let's see if it works. I don't know why that one little section is not working today. Oh, well. Hi. And now I'll go back over here. Hey, Brad. Oh, were you just stretching her? If we have time at the end. Yes, sir. Okay. Over 8. All right, so what am I going to get when I push enter? Okay. So I'd probably go ahead and say 5.890. Okay. About 5.890 radians per second. Angular velocity is how fast the angle is increasing with respect to time. Okay. Now, you remember in one full revolution, how many radians is that? It's 2 pi, right? So 6.28. So in this particular example, the 5.89 is very close to 6.28. So this is almost getting a full revolution every second. Okay? So let's kind of sum everything up real quick. Linear versus angular velocity. When you see V, okay, we know that that's going to represent linear velocity. The dimensions are always length per unit of time. So feet per second, miles per hour, meters per minute. The numerator units are always measures of length. Okay. Now for angular velocity, we have this curvy little W right here. What do we call him? Starts with the O. Omega. He's the Greek letter omega. It has dimensions of radians per time, just like I told you a second ago, always radians per time. So revolutions per minute, radians per second, even degrees per hour. Because at this point, are degrees and radians, can they be equivalent? Yeah, we can convert between one to the other, so absolutely, absolutely. The numerator units are angle measurements. Okay, so let's try a little more dimensional analysis. Convert 60 RPM, revolutions per minute, to radians per minute. Okay, so let's go ahead and start with what we have. I'm going to set up my fraction. 60 revolutions per minute. So 60 revolutions in 1 minute. Okay. Now, we definitely want to keep the minute, but we want radians per minute. So what's the one thing we want to get rid of? The revolutions. Okay, so if I want to get rid of the revolution, then that means he has to be here, right? So let's think about one revolution. And we actually just said this a second ago. How many radians are in one revolution? 2 pi. There you go. 2 pi radians. So now we see that the revolutions cancel. You've got radians per minute. That's what dimensional analysis is. It's putting in fractions to change whatever units of measurement you have. Okay. So 60 times 2 pi would give me, 120 pi. And let's approximate that. Why not? Because I'm going to give pi another chance. I mean, dang it. Forgot I was recording for a second. Does remind me of a good joke, though. Okay, two fish are swimming along. One of them suddenly hits a concrete wall. Damn! It's damn. Yeah, there you go. Yeah. I just kind of came up with that one for the halibut. The halibut is a type of fish. Halibut. I did it for the halibut. For the hell of it. There you go. There you go. There you go. Yeah. It was an act of cod. Hey, look, math. Okay. So with the .99, I would definitely feel comfortable just saying 377. So 377 radians per minute. Okay. Now, the one thing, this is kind of foreshadowing what's going to happen. This guy right here, that fraction. When you're talking about solving angular and linear velocity problems, that exact fraction, you're going to be seeing him over and over and over again. Because angular velocity has to be in radians. So that's the first thing we're always going to do is convert whatever we start with. Okay, well, let's try 6b. I want to change, again, the same thing, 60 revolutions per minute. So 60 revolutions in 1 minute. I want to change it to, this time, degrees per second. So now I not only have to change the minutes, I want to get rid of the revolutions. I want to change that to degrees. Okay, so there's going to be two other fractions that we're going to tack onto this guy. All right, so take about a minute. Let's see if we can all come up with the same thing. So we don't want radians this time. We want degrees. We want those revolutions to drop out. I don't want minutes. I want seconds. And remember, the order in which you do these does not matter because the multiplication is commutative. Okay, so you could take and get rid of the revolutions first, or you can go ahead and convert the minutes first. It's whichever you want. Is everybody about ready, or we need a few more seconds? Okay. So what do you want to take care of next, the revolutions or the minutes? The minutes, okay. So if I want to take care of the minutes, if I want that to be seconds, just like we've seen before, yeah, 1 minute is 60 seconds. So now it's going to be in revolutions per second. So now we got to get rid of revolutions. You're absolutely right. We got to put radians over the revolution. And we've seen it before. Yeah, I want to change the degrees. Yeah. There you go. You want degrees, and it's 360 degrees in 1 revolution. I got off on that, sorry. Degrees in 1 revolution. And that's the same. We know there's 2 pi radians in 1 revolution in the previous problem. There's 360 degrees in 1 revolution here. So the revolutions cancel. The minutes cancel. And do you notice something else? The 60s cancel as well. So this one, actually, again, another one, we don't have to go back to the calculator. It's in degrees per second. So it should be what? 360 degrees per second. Okay. Is everybody okay with the dimensional analysis? Anybody having problems? Okay. All right. Yes. Oh, because see, if I go ahead and leave it as is, it's in revolutions per seconds, and I want degrees per seconds. So I know that I got to get rid of the revolutions, so I got to put the revolution down here. So we just go ahead and do the same thing we did in the previous problem. Let's go ahead and say that's 1 revolution, but this time in degrees, it would be 360. All right. So all those previous formulas, okay, we can use the previous ones to find a relationship between linear velocity v and angular velocity omega. So this is the one, if you're wanting to use the formula, this is what you're going to go ahead and do. But honestly, this is one of those times where I never really start from the formula. I always start from one fraction. Always, always, always is going to be the same. Okay? Because these problems, you know, whatever you're talking about out in the real world, it's really anything circular. You could be talking about a Ferris wheel, you know, the speed at which it's turning. You could be talking about a DVD and a player. I mean, really anything circular. So for these problems, always go ahead and start with this information. The number of revolutions over time. Okay, the number of revolutions always over time. But now remember, we always want to find the angular velocity first. The only way you can get linear velocity is by first finding the angular velocity. But you remember I said a little while ago, we always like our angular velocity to be in what? We want them to be in radians. So you remember that one fraction I said that was going to be really important to you? Whatever you start the problem with, you'll now go ahead and say times 2 pi radians over, what was it? 1 revolution. Because the revolutions cancel, you've got radians per time. If you do this, that immediately gives you omega, your angular velocity. Okay. The most important information you need is just the number of revolutions in the amount of time given. You multiply that by 2 pi radians over 1 revolution, that is angular velocity guaranteed. Now, there's only one thing you have to do in order to change this into linear velocity. And take a look at the formula. What is it? What do I have to multiply omega by? I got to multiply by the radius. That's exactly right. So this right here, if I simply go ahead and multiply by the radius, this now becomes v, my linear velocity. That is the only thing. And that's why you always have to have the angular before you can find the linear. The second you multiply by the radius, you no longer have angular, you have linear velocity. And now you have an actual measurement. Okay. And all of these problems can be started the same way. Okay. I think it just makes it a lot easier if you kind of think of it in this terms. But if it helps you to just go straight from the formulas, please, you know, whatever works best for you. So let's take a look at some examples. This is where that other page comes in. So we're going to talk about some vinyl records for a second. And I think we'll have just enough time to at least get this first one started. Okay. And I'm actually learning something myself today, that vinyl records are making a comeback. How many people in here have purchased some vinyl records? Really? Really? And they're over current artists.
Yeah, current artists, and they're also like Michael Jackson, like
Wow.
classical music. So I sound like a garage sale.
So that's cool. That's cool. That's really cool. Okay. Because my dad has a huge collection of vinyl records. I'll have to look through them. Okay, so let's try number 1. It says a typical vinyl record has a diameter of 30 centimeters. When played on a turntable, the record spins at 33 1/3 revolutions per minute. And remember, these problems always start with the number of revolutions over time. Okay. Now this one, you know, we're going to have to kind of approximate it. I know that 1/3 is 0.3 repeating, but for our purposes, we'll just go ahead and say 33.3, because in A, we want to find the angular speed. Okay. So we're going to start with 33.3 revolutions per what? In 1 minute. You always start these problems with the same ratio, the number of revolutions over time. But we like our angular velocity to be in radians. So there's that fraction, the 2 pi radians over 1 revolution. You're going to use him a lot. times 2 pi radians over 1 revolution. Now, so you'll notice your revolutions cancel. You've got radians per minute, which is exactly what the problem wants. All we have to do is multiply that out. You've got your angular velocity. Okay, remember that's omega. Okay, so let's see here. 33.3 times 2. We'll try it one more time. Hey, it worked. Once. Okay. So let's say that my angular velocity, the rate at which the angle is increasing with respect to time, is 209.2. Okay, so about 209.2 radians per minute. Okay. Now B wants me to go ahead and find the linear speed. Okay. There you go. Once you have the angular velocity, remember omega, all you have to do is multiply him by the radius. You have your linear speed. What is the radius? 15. Okay. So they gave me a diameter of 30, so the radius has to be 15 centimeters. So I'm going to go ahead in B, take what we had here. I'm going to start with the angular velocity, 209.2 radians per 1 minute, and I'm going to multiply it by the radius. Now, when I do these types of problems, I always like to go ahead, because a lot of times you're going to have more than one fraction. So I always take the radius and just put it over 1. So in this case, 15 centimeters over 1. Okay. Now, should I stop there? If I stop here, it's going to be in centimeters per minute. What is the question asking for? There you go. So we still want centimeters, so I'm not going to alter him, but we want it per second. So I'm going to have to tack on another fraction. In fact, what would it be? 1 minute over 60 seconds. I'd have to put the minutes on top because I want those to cancel. Now here's the thing about the radians. Once you go ahead and multiply by the radius, see, the radius is always going to have a unit of measure with it. So the radians kind of just disappear because now they have a length that you can associate with them. Okay. So all we have to do is take 209.2 times 15 and then do what? Divide by 60. Okay. So let's see. I'm going to take the previous one. 209.23 times 15 divided by 60. So how many centimeters per second? About 52.3. Okay. So it's traveling pretty quick. 52.3 centimeters per second. I guess you could say that's the vinyl answer. Oh, really? Just, no? Just go straight to it? Okay, Brandon, what's up? What's your question? Honestly, I don't know what a typical turntable spins at. Do you happen to know, Mr.? I don't know. That's a good question. Yeah, you can speed them up, and it sounds like the Chipmunks, or you can, slow it down. Oh, there you go, yeah. And then you could, scratch the record up pretty bad. So, okay. All right, so how are we doing on linear and angular velocity? Okay, I mean, we've really only got through one problem. So, tomorrow we'll go ahead and do a few more. We'll see what you guys think. Okay, so good.